Good morning students, this is Latif sir. Today I am going to discuss about some P block element. This is the chapter 11 of class 11th chemistry. The topic is some P block elements. Okay, and in class 11 you have to read only about group 13 and group 14. Group 13 elements, that is boron family, and group 14 elements a carbon family. And this is the reduced syllabus. According to the reduced syllabus you have to read about general introduction. From group 13 you have to read about general introduction, electronic configuration, occurrence, variation of properties, oxidation state, trends in chemical reactivity, physical and chemical property, and preparation of some compounds like boric acid, alums, okay, and Lewis acid character of boron halide, and amphoteric nature of aluminium. This is the reduced syllabus. And from group 14 elements you have to read about general electronic characteristic, electronic configuration, occurrence, variation of properties, oxidation state, trends in chemical reactivity, and preparation of some compounds like silicon carbide and silicone. Okay, their preparation and use. So first you have to read about group 13 elements or boron family. Group 13 or boron family. Okay, and the first member of this group 13 element is boron. Boron, aluminium, gallium, indium, and thallium. Boron, aluminium, gallium, indium, and thallium. This is the group 13 element. Boron, aluminium, gallium, indium, and thallium. And their general electronic configuration is NH2. The outermost electronic configuration is NH2 NP1. Okay, all these elements have same outermost electronic configuration, which is NH2 NP1. Okay, now see the electronic configuration of boron, which is helium 2s2 2p1. Helium 2s2 2p1. Electronic configuration of aluminium is neon 3s2 3p1. Atomic number is 13. Gallium atomic number is 31, and electronic configuration is argon 3d10 4s2 4p1. See, 10d electrons present. 10d electrons are present in gallium. 10d electrons are present in the inner 3d orbitals of gallium, but there is no d electron present in aluminium. Okay, remember that 10d electrons are present in the inner orbital of gallium. And now electronic configuration of indium, which is 4d10 5s2 6 5p1. 5s2 5p1. Here also 10d electrons in 4d orbital. And electronic configuration of thallium TL, atomic number 81. The electronic configuration is xenon 5f 4f14. Okay, 5d10 6s2 6p1. Electronic configuration of thallium is xenon 4f14 5d10 6s2 6p1. And in thallium there are total 14 f electrons are present. 14 f electrons in 14 f electrons are present in inner 4f orbital, but there are no f electrons. There is no f electrons, that is electron in f orbitals, are present in indium and gallium. Okay, from gallium, indium, and thallium, if you see, 10d electrons are present in gallium, and 10d d electrons are present in indium also in 4d orbital. And in case of thallium 14 f electrons are present in inner 4f orbital of thallium. Okay, so electronic configuration, enthalpy, variation of ionization enthalpy, and their values are given in this table. Okay, melting point, boiling point, their radius, and you can see radius of ionic radius and atomic radius also given. Both are given. Atomic radius of boron is 88, atomic radius of aluminium is 143, and while atomic radius here one deviation is found, which is atomic radius of gallium is less than that of aluminium. This is the question. why atomic radius of gallium is less than that of aluminum. Generally we know down the groove atomic size increases, but in this case there is a deviation. That is, the deviation is the atomic radius of gallium is less than that of aluminum. You have to know the answer. I will discuss later. Okay. And then atomic radius of indium is 167 and atomic radius of thallium is 170. It is increases from top to bottom, but deviation is found in between aluminum and gallium. Okay, so first, group 13 element, boron group, boron, aluminum, gallium, indium and thallium. Okay, boron is typically non-metal, aluminum is a metal, but so many chemical similarities to boron and gallium. Indium and thallium are almost exclusively metallic in character. Okay, boron is fairly rare element, mainly occur as orthoboric acid, that is H3BO3, and borax Na2B4O7.10H2. These are some chemical compounds of boron. Okay, and aluminum exists as a bauxite Al2O3.2H2O. Now electronic configuration, I have already told electronic configuration of all group 13 elements, generally outermost electronic configuration, which is NH2NP1. NH2NP1. Okay, so a close look at the electronic configuration suggests that while boron and aluminum have noble gas core, gallium and indium have noble gas plus 10d electron. In boron and gallium, in gallium and indium there are total 10 inert d electrons, and in thallium has noble gas plus 14 f electron plus 10 d electron. I have already discussed this one. Okay, so atomic radii. Okay, on moving down the groove on moving down the group, for each successive member one extra cell of electron is added, and therefore atomic radius is expected to increase. However, a deviation is can be seen, and you have to remember the deviation can be seen, and the deviation is atomic radius of gallium is less than that of aluminum. I have told before some time that is the deviation, and you have to know the cause of this deviation. The cause is due to presence of inner 10 3d electrons, d electrons in inner 3d orbital in case of gallium. This is the cause, because d orbital electrons has a lower screening effect. Okay, and due to this low screening effect, the atomic radius of gallium become less than that of aluminum. Okay, so this can be understood from the variation in the inner core of the electronic configuration, and the presence of additional 10d electrons offer poor screening effect for the outer electron from the increased nuclear charge in gallium. I have told, due to presence of poor screening 10d electrons in gallium, which offer only poor screening effect for the outer electron from the increased nuclear charge in gallium. Consequently, atomic radius of gallium is less than that of aluminum. Okay, now see ionization energy. The ionization enthalpy value, as expected from the general trend, do not decrease smoothly down the groove. The decrease from boron to aluminum, first it decreases from boron to aluminum, is associated with increase in size, and the observed discontinuity in the ionization enthalpy values between aluminum and gallium. There is also one deviation in ionization enthalpy between gallium and aluminum. And another deviation between indium and thallium. These deviations are due to inability of D and F electrons present in the inner core. Okay, so uh, this deviation are due to inability of D and F electrons which have low screening effect to compensate the increased nuclear charge. The order of ionization enthalpy, or the order of ionization enthalpy, as expected, that first ionization enthalpy is less than second ionization enthalpy, which is less than third ionization enthalpy, and the sum of the first three ionization enthalpy for each of the element is very high. Now electronic configuration down the groove, electronic configuration, electronegativity down the groove. Electronegativity first decreases from boron to aluminum and then increases marginally, and this is because of discrepancies in atomic size of the elements. Physical properties: boron is non-metallic in nature. It is extremely hard. It is extremely hard and black colored solid, and it is exist in many allotropic forms. And due to very strong crystalline lattice, boron has unusually high melting point, and rest of the members are soft metal and low melting point and high electrical conductivity. And the melting point of the boron, aluminum, gallium given here you can see. Okay, general physical properties of the group 13 elements. And density of the element increases down the group from boron to thallium. Now chemical properties: oxidation state and trends in chemical reactivity. Now see general chemical properties. First, oxidation state and trends in chemical reactivity. Generally group 13 elements, group 13 elements, so two types of oxidation state, one is +3, another is +1. Okay, so due to small size of boron, the sum of first three ionization potential is very high, and this prevent to form +3 ions and force to form only covalent compounds. But as we move from boron to aluminum, the the sum of first three ionization enthalpy of aluminum considerably decreases and is therefore able to form +3 ions. Okay, that means aluminum can form +3 ion easily. Okay, in fact aluminum is highly electropositive metal. However, down the groove due to poor shielding effect, this is important, down the groove due to poor shielding effect of intervening d and f orbitals present in gallium, indium, thallium, due to presence of this lower screening or poor shielding effect of intervening d and f orbitals, the increased effective nuclear charge holds the outermost two electrons in ns orbital. That is, uh, the increased effective nuclear charge holds the outermost ns electrons tightly. Okay, that means this outermost ns two electron in ns orbital, outermost ns orbital, these two electrons do not take part in bond formation. These two electrons become inert due to presence of inert d and f electrons in boron, in gallium, indium, and thallium. That means the outermost ns electron become inert, and this effect is known as inert pair effect. Okay, so down the groove, the formation of +1 oxidation state is down the groove, the +1 oxidation state become more stable than +3 oxidation state. The reason is that due to presence of intervening D and F orbitals. Low screening or poor screening D and F electrons in gallium, indium and thallium. In gallium and indium no F electron, but in case of thallium there are 14 F electrons are also present. Okay, so thereby restricting their participation in bond formation, in bonding. As a result, only p electrons may be involved in bond formation in case of, this is in case of thallium. Okay, in fact gallium and indium and thallium, in fact gallium, indium and thallium both +1 and +3 oxygen state are observed. Both +1 and +3 oxygen state are observed, but the relative stability of +1 oxygen state progressively increased for heavier elements. That is the formation of that is the relative stability of +1 oxygen state increases from aluminum to gallium, gallium to indium, indium to thallium. Okay, that means only thallium shows only +1 oxidation state, while boron, aluminum, this can show and the most common oxidation state of boron and aluminum is +3, and gallium and indium can show both type of oxidation state, that is +1 and +3. Okay, so in thallium +1 oxidation state is predominant, and in whereas the +3 oxidation state is highly oxidizing character. Now see the trivalent state. Trivalent state, in trivalent state generally boron and aluminum can exist in +3 oxidation state, and thallium generally exists in +1 oxidation state. Okay, due to inert pair effect, and and the cause of this inert pair effect is due to presence of inert D and F electron in gallium, indium and thallium. And in thallium the effect is found more. This is because in thallium there are 14 F electron and 14 and 10 D electrons are also present, and the low or poor screening effect due to poor screening effect of inert 3D, inert D and F electrons, we observe this inert pair effect. So trivalent compound of boron, that is halide of boron, that is boron can form compound with halogen like BCl3, BF3, Bi3, like this, BBr3. And in this compound boron has only 6 valence electron. So in trivalent compound of boron, the boron has 6 electron, only 6 electron in the valence shell. Thus BCl3, BBr3, BF3, these are electron deficient molecule, and these molecules can act as Lewis acid because they have there's incomplete octet. Okay, so such electron deficient molecule like BCl3, BBr3, as they have only 6 electron in the valence shell, such electron deficient molecule have tendency to accept a pair of electron to achieve stable electronic configuration and thus behave as Lewis acid. Okay, thus BCl3 can form compound with ammonia, NH3, Lewis acid and Lewis base compound, and the tendency to behave as Lewis acid decreases with increase in size down the group. BCl3 easily accept a lone pair of electron from ammonia to form BCl3.NH3. This compound is formed because BCl3 act as Lewis acid, and they can also act as dimer. They can easily form dimer to overcome this electron deficiency. Now reactivity of group 14 elements, group 13 elements. Reactivity towards air. This element reacts with air, that is oxygen and nitrogen, to form oxide and nitride. For example, when boron reacts with oxygen, it forms B2O3. When aluminum reacts with oxygen, it forms Al2O3. Okay. Similarly, when boron reacts with nitrogen, it forms boron nitride Bn. When aluminum reacts with nitrogen, it forms aluminum nitride Aln, like this. And reactivity towards acid and alkali. And boron does not react with acid and alkalis even at moderate temperature, but aluminium dissolve in mineral acid and aqueous alkalis, and thus shows amphoteric character. You have to remember this. You have to read about amphoteric character of aluminium. This is given in the syllabus. Okay, that means aluminum can react with both acid and alkalis. So when aluminum reacts with dilute acid, dilute HCl, it will form Al3 plus, that is AlCl3, and hydrogen gas. And hydrogen, the reaction is 2Al plus 6HCl implies AlCl3, or you can also write 2Al3 plus 6Cl minus plus 3H2 gas. And aluminum can also react with aqueous alkali to liberate dihydrogen H2 gas, and the reaction is Al plus NaOH plus water, aqueous solution of sodium hydroxide, to give sodium tetrahydroxoaluminate, that is NaAlOH whole 4 plus 3H2. Okay, so this reaction proves amphoteric nature of aluminium. And reactivity towards halogen, I have already told. Group 13 elements form halide like EX3, that is BCl3, AlCl3, BF3. Okay, and these halides, trihalide of group 13 elements, act as Lewis acid. And tendency of Lewis acid character decreases down the group. Okay, and now some chemical compounds of group 13 elements. First is orthoboric acid. The formula is, or it is also called boric acid, H3BO3. H3BO3, it is a white crystalline solid with soapy touch and sparingly soluble in water and highly soluble in hot water, and can be prepared by acidifying aqueous solution of borax. So you have to remember the preparation of boric acid. Okay, so you can prepare boric acid from borax. Borax is Na2B4O7. When borax is treated with hydrochloric acid, aqueous solution of hydrochloric acid, you will get sodium chloride and boric acid, BOH whole thrice, which is actually H3BO3, boric acid. Okay, so you can prepare orthoboric acid or boric acid from borax, and boric acid can be prepared by acidifying an aqueous solution of borax. The reaction is Na2B4O7 plus 2HCl plus 5H2 arrow 2NaCl plus 3BOH whole thrice. Now structure of boric acid, it is given, and you have to read the heating effect on boric acid. On heating orthoboric acid above 370 Kelvin, it forms metaboric acid, and the formula is formula of metaboric acid HbO2. And on further heating, metaboric acid yields a boric oxide or boron oxide B2O3. Heating effect on boric acid or orthoboric acid, and this is the structure of boric acid H3BO3. Okay, this is the polymeric structure of boric acid. Now, why boric acid considered as weak acid? This is because it is not able to release H plus ion on its own, and it receives OH minus ion from water molecule to compensate its octet, and in turns releases H plus ion. That's why boric acid is known as weak acid. Next chemical compound is alum. The formula of alum is K2Al2SO4 dot 24H2O. Potash alum, this is the formula of potash alum. Alum are double salt. An example of alum is potash alum, like potassium aluminum sulfate K2SO4 Al2SO4 dot 24H2O. Okay, and potash alum and ammonium alum, ammonium sulfate AmNH4 whole twice SO4 dot Al2SO4 whole thrice dot 24H2O, or chrome alum K2SO4 dot Cr2SO4 whole thrice dot 24H2O. And preparation of alum uh, you have to read this reaction. On K2SO4 dot Al2SO4 whole thrice and 4 LOH whole thrice plus 6H2SO4, you will get K2SO4 Al2 3 Al2SO4 whole thrice 12H2, or K2SO4 Al2SO4 whole thrice, that is potassium sulfate plus aluminum sulfate reacts with the water, it forms potassium K2SO4 Al2SO4 dot 24H2. These are the preparation. Okay, so when alum stone is treated with excess, alum stone is treated with excess of sulfuric acid, the aluminum hydroxide is converted into aluminum sulfate, and a calculated quality of potassium sulfate is added, and the solution is crystallized to generate potash alum. And use of potash alum, it is used to for purification of water. It is also used for water proofing and textiles. Okay, there are some use of potash alum. You have to remember preparation of potash alum and use of potash alum only according to reduced syllabus. And preparation of orthoboric acid and use of orthoboric acid, heating effect on orthoboric acid. Okay, in the next video I'll discuss about group 14 elements, that is carbon group.